Let's take a look at the previous graph. If we were asked to determine for what x values the function was greater than or equal to 0, we would essentially have to look for all the values that are above this line. So, the x values for which the function is greater than or equal to 0 are all the points from -3 to 7. But we do have a hole here, so we have to exclude that from our values. So it's going to go from -3 up until this hole, which is at 2, -2, continue from -2 up to 7. And these are the values for which the x values for which the function is greater than or equal to 0. If we wanted to ask the question for which the x values were strictly greater than 0, then that would exclude all the x-intercepts, which is this point right here. And that would mean that we would have to create a hole at that point. So the x values for which that function is strictly greater than 0 is similar to the previous one, where we had that our function is going from -3 to -2. But since there is a hole now at 2, it's going to go from -2 to 2 and then resume from 2 to 7. So both these cases were similar, with the exception of including or excluding the x-intercept. But to determine the x values for which the function was greater than or equal to 0, we had to actually determine the vertical asymptotes, the holes, and the x-intercepts. So these are something called our crucial points in order to determine the parts for which the function is greater than or equal to 0. Let's take a look at a few examples. If we look at this first case, you can tell that it's a linear function, so that means it has no vertical asymptotes or holes. And so all we have to do are look for the x-intercepts, which basically mean to just solve for x. So if we solve for x in this case, I personally like to bring all the x values to the left-hand side because it makes it a little easier to graph. So if we subtract 4 to both sides and just do the math, we get -4 minus 4x minus 4x, and get that -2x plus 5 is greater than or equal to 11, -11. So we have to subtract 5 to both sides, subtract 5 to both sides, and we get -2x is greater than or equal to -16. By dividing -2 to both sides, we know that when we divide a negative number, the sign of the inequality flips. So this is going to be x is less than or equal to 8. Since it's less than or equal to 8, 8 is being included, and it's all the x values that satisfy it are anything to the left of 8. In interval notation, this would just be anything from -infinity up until 8, and this is going to be a bracket since it's being included. So this is our solution. In this next example, we have a quadratic inequality. What this means is that it is going to have x-intercepts, and again, it has no vertical asymptotes or holes because it's a polynomial. So to find the x-intercepts, we have to just set the function x squared minus 3x minus 4 equal to 0 and solve for x. In order to do that, we can factor this. So we would have x minus 4 and x plus 1, because -4 times 1 is -4, and -4 minus plus 1 is 3, -3. So setting this equal to 0, we have that x is equal to 4 and x is equal to -1. So these are our crucial points, and we have to figure out in which portion of the interval the function is greater than or equal to 0. Since -1 and 4 are included, because they are x-intercepts and it can be greater than or equal to 0, those points should be filled in. But now let's do test points. So we're going to pick an x value that is to the left of -1. Anything to the left of -1, let's say -2, so let x be equal to -2. Something between -4 and -1, that's 0, so let x be 0. And anything greater than 4, so let's pick 5. So let x equal 5. So these are going to be our cases. So we're going to plug these x values into our original function. So we're going to have -2 squared minus 3 times -2 times minus 4. And we're going to see if that is greater than or equal to 0. So we get that in fact 6 is greater than or equal to 0, so that checks out. We can do the same for all the rest of the x cases, so we can go ahead and do that. So we get that -4 is greater than or equal to 0, which is not true, so this interval doesn't work. And then in this final interval, we get that 6 is greater than or equal to 0, which is also true. So the only intervals that work are from -infinity to 1 and from 4 to positive infinity. So let's write these intervals out. It's going to be from -infinity to -1, which is being included, and from 4 to positive infinity. If we take a look at the actual graph, we can indeed see that the graph is greater than or equal to 0 for all the points from -infinity to 1 and then from 4 to infinity. In the following example, we actually have a rational function, which means it might possibly have wholes, x-intercepts, and vertical asymptotes. The easiest way to see if it has any of these would be to factor it completely. So if we factor this, we would have x on the numerator, and we have to think of two numbers that multiply to give you 6 and add up to give you -5. So that would be -2 and x -3. In the denominator, we can factor out an x, so we would be left with x minus 5 inside parentheses. And by looking at this, we can actually see that there is nothing that simplifies out or cancels out. This means that there are no wholes. But now let's look at the x-intercepts. Remember that to find the x-intercepts, we have to set the numerator equal to 0. So we have that x minus 2 times x minus 3 is equal to 0. And solving for x, we get that x is equal to 2 and x is equal to 3. To find the vertical asymptotes, we would have to set the denominator equal to 0. And since we already have the factored form, we can use that. So we have that x times x minus 5 is equal to 0. And solving for this, we have that x is equal to 0 and x is equal to 5. So 0, 2, 3, and 5 are our crucial points, and we have to test the intervals in between them. So let's pick x values in between each of these points. An x value before 0 would be -1. An x value between 0 and 2 is 1. An x value between 2 and 3, we can pick 2.5. Another between 3 and 5 is 4, and the value after 5 is 6. Because 2 and 3 are x-intercepts, those will actually be included in our solution. And since 0 and 5 are vertical asymptotes, those will not be included. So by plugging in our x values into the original function, we can see whether or not the intervals are satisfied. So if we can plug in -1, so -1 squared minus 5 times -1 plus 6 all over -1 squared minus 5 times -1, and we were going to see if that is greater than or equal to 0. Let's see. So by combining everything or putting it into your calculator, we get that this side is 2, which is greater than or equal to 0, so this interval works. On this side, we're going to have -1/2, which is not greater than or equal to 0, so this interval does not work. In this middle interval, we have 1/25, which is greater than or equal to 0. That checks out. In this other interval, we have that 1/2 is greater than or equal to 0, which is not true because of the negative sign. And in this final interval, we have that 2 is greater than or equal to 0, which does check out. So the only intervals that work, the intervals where the function is greater than or equal to 0, are from -infinity to 0, which is not included because that's a vertical asymptote, and then from 2 to 3, which are included because they are x-intercepts, and from 5, which is not included, up until infinity. From the graph, we can also see that the function is greater than or equal to 0 on those specific intervals only. So this is our solution.